So let us recall what we have did in the previous lecture. In the previous lecture, we have defined a continuous function, and from that we have discussed the related some equivalent condition on continuous function. So that conditions, let us state that if f is a continuous function at point x is equal to a, where f is a map from x to y, where x and y are the matrix spaces and your point a is belongs to x. So the first statement is says that f is continuous. The second statement is says that for every epsilon greater than 0, there exists a delta greater than 0 such that d1 of x comma a is less than delta, implies d2 of f of x comma f of a less than epsilon. So this is the second statement, which is the actually definition of continuous function, which can be also stated as for every epsilon greater than 0, there exists a delta greater than 0 such that x belongs to this neighborhood. That means s delta of a, which implies f of x is belongs to the neighborhood of f of a. The fourth statement is equivalent to this definition. It says that the inverse image of f of any open sphere s epsilon of f of a about f of a contains an open sphere s delta of a. That means it is about a. That means it says that for every epsilon greater than 0, there exists a delta greater than 0 such that s delta of a is a subset of f inverse of s epsilon of a. And the fifth condition, or I can say statement, it says that if xn is a sequence in x and this xn is a converge to a as n tends to infinity, implies f of xn will converge to f of a as n tends to infinity. In the previous lecture, we have stated that this all 5 statements are equivalent. Any one of them you can use to prove any function is continuous or not. And then we have discussed about the composition of two continuous function is continuous. We have proved, or I gave you as an exercise, that the sum of two continuous function is continuous, product of two continuous function is continuous, and the division of two continuous function is continuous, provided that the denominator function is non-zero. And then we have solved certain examples related to it. In this lecture, we'll discuss very important results on this continuous function. This is the another equivalent condition for continuous function. That means we have these 5 conditions are already there, and we are established 2 more conditions which are equivalent to a continuous function. So that says that, let us say that theorem is, let x1 comma d1 and x2 comma d2 be a matrix space. So we have given these 2 matrix spaces, and f is a function from x1 to x2. Then prove that f is continuous on x if and only if f inverse of g is open in x1 whenever G is open in x2. So ultimately it says that the inverse image of open set is open. If f is continuous on x, so it says that the inverse image of open set is open. So that is also I can write down, it is if and only if, that means f is continuous on x if and only if I can say that the inverse image of every open set in x2 is open in x1. So this is the alternating statement we can write. So any one of them. So ultimately now this is the sixth statement you will have regarding the this 5 statement is there, and then the sixth one is this. That means fx continues on the space x. It says that the image, inverse image, not image, here it is inverse. How forward? Inverse image of, that is f inverse of G, is open for every open sphere or open set in x2 is open in x1. Let us try to prove this statement. So let f be a continuous function on x1. That is our supposition for proving this side. That is, f is continuous on x1, we have to prove that the inverse image. So we must show that if G is open in x2, and suppose that G is open in x2. Now we shall show that f inverse of G is open in x1. We shall show that f inverse of G is open in x1. So whenever you have to prove something is open, you have to start as per the definition. For every point in this set, there exists some neighborhood of that set which contains inside this set. So that is the definition of open set. So I'll start with for any x in this set f inverse of G. So what we need to find out, what we have to find an open sphere of x such that SR of x, the open sphere which is SR of x, is a subset of f inverse of G. This is our objective. So as this x is belongs to f inverse of G, will implies f of x is belongs to G. Now what is G as per our assumption? A G is open in x2. So that means according to that, what we can say is there exists some neighborhood of this f of x there exists an open sphere of f of x such that the open sphere of this f of x, that is will denoted by SR1 of f of x, is a subset of G as per the definition of G is open in x2. Now what is given, this is also our assumption that f is continuous on x1 to x2. So for that, since f is continuous from x1 to x2, what we can say as per the equivalent condition, that is this one, it says the inverse image of f for any open sphere, that is S epsilon f of a about f of a, contains an open sphere S delta of about a. So we have already this here, that is this sphere. It says that this sphere for every epsilon or every open sphere, inverse image of this sphere will contain some open sphere of x. So as since f is continuous and we are using that equivalent condition, then the inverse image of any open sphere, in particular SR1 of f of x about f of x, contains an open sphere SR of x about x. So this open sphere contains by the inverse image of this open sphere. So that means I can write down that SR of x is a subset of f inverse of SR1 of f of x, which will be the subset of f inverse of g because of this previous statement. If I apply f inverse here, we can have this f inverse of this quantity will be a subset of f inverse of this set. So therefore we can say that this, and therefore we can say that there exists r greater than 0 such that SR of x is a subset of f inverse of g. So therefore we can say that f inverse of g is open in x1. So which proves that f is continuous implies inverse image of an open set is open. Now conversely, suppose that means we are doing this side now. Suppose that f inverse of g is open in x1 whenever g is open in x2. What to prove? Our objective is to prove that f is continuous on x1. So it is sufficient to prove that for every point in this it is continuous. Well, right, it is sufficient to prove that f is continuous at any point a belongs to x1. So what we'll start with? We'll start with, ultimately I am using the previous result which we have used, that is the inverse image of a sphere, that is the fifth statement that we have here, sorry, fourth statement. So for any open sphere of this about f of a contains, so we'll prove this statement. So I will start with this open sphere. I'm considering an open sphere of f of a. So let SR of f of a be an only open sphere about f of a. then what we can say, SR of f of A is an open set in X2. As per the every open sphere is an open set, which we already proved. As per this argument, G is open in X2. We say that F inverse of G is open in X1. So this is an open set in X2. So we can say that F inverse of this set is open in X1. So therefore, we can say that F inverse of SR of f of A is open set in X1. Now, since this is open, there exists some open sphere of this which is contained by this. So since F inverse of SR of f of A is an open set, there exists an open sphere SR of A or R1 of A, that is some another is there, such that SR1 of A is a subset of F inverse of SR of f of A. And this is exactly the equivalent condition on open continuous function at A. So therefore, this we can say that F is continuous at A, and therefore the result is proved that F is continuous if and only inverse image of an open set is open. Now we'll discuss some examples which can be used to derive or to discuss some counter example for certain things. So in that, the first example says this: every subset of R with the discrete metric space is open. Ultimately, I want to prove this statement, and from this statement I will prove that any map, if I given you on discrete metric space, then that map is always an open map. Okay, so let us give the solution for this statement first. So what it says that if you have any subset of R with a discrete metric space is always an open. So let us say if FA belongs to R and a D is a discrete metric on R. Let us consider this. Then what is the open sphere of this A with radius 1? Then we know that it is X, set of all X, such that it is the distance between X and A is less than 1. But as per the definition of a discrete matrix, it says that for every xy, we have two conditions is there. Either it is 0 if x is equal to y, it is 1 if x is not equal to y. So as per this argument, how many points contains by this? It only contains a 1 point. That is a center of that set, this point. Because otherwise it will be, if it is less than 1, only one possibility is there, 0. That's why it is x is equal to A is there. And we know that this open sphere is always open set. So we can say that S1 of A is equal to this singleton A is an open set in R. with a discrete matrix D. So what we can say, the only one point in it or I can say that not this one, but I can have the subset. Let A be a subset of this R, comma D. Then I can write A is a union of all the singleton sets where A is belongs to A. And we have already proved that the arbitrary union of open set is always open because singleton set is open in this space. And so as per that result, we can say that this A is also open and A is any subset. I have taken A is any subset. So it's proved that any subset of discrete matrix space is open. So let us write that things which we have explained you. Since any arbitrary union of open set is open, therefore A is open. Due to that, because every singleton set is open in this space. So it proves that every subset of R with a discrete metric is open subset of R. Now, with the help of this example, we can have the another example. We say that let X be an infinitely many or infinite discrete matrix space. That means a set X contains infinitely many points. Then prove that every map F from X to a matrix space Y is continuous. So it says that if you have X, which is infinitely many points, and it is a discrete matrix. Okay, and then you define any map from X to Y, which is always continuous. I think so. In one of the lectures, some of them have asked you about this one. That means if I define a function which is on discrete matrix space, then it is always continuous because every subset of X is open. See, in the previous example, if you replace this R by X with infinitely many points, then nothing will change here. Everything is same. So with this note, if you consider that previous result, that we know that why we know because of previous result, because you have to write down all the details which we have did in the previous result. Every subset of X is open set. Now I want to prove that this F is continuous. So I have to prove that every open sphere in Y, its inverse image will be open in X. So I'll start with let G be any open subset of Y. Therefore, what we can say is F inverse of G is a subset of X. And since F inverse of G is subset of X, and we know that X is a discrete matrix, so any subset of X will be open. So therefore, we can say that F inverse of G is open in X. So which proves that if G is open in Y implies F inverse of G is open in X under the discrete matrix space. Therefore, F is continuous on X with a discrete matrix. So if any discrete matrix is there, then we can say this. Now, very interesting fact we have that we can say that inverse image of an open set is open. Can we say that the image of an open set is open? That is the question. That under the continuous map is, or I can say if F is continuous from X to Y, so it is a continuous function. And if G is open in X, will it implies F of G is open in Y? So this is a question I'm asking you. Will it be this is true? So it says that the image of an open set is open because this is the open set in X. The image of G is F of G. Is it be open in Y? The answer is no. The hint is previous example. If I consider the F, which is the discrete matrix space, okay, then we know that every open sphere or every open set, every subset of this X is open. But Y is not a discrete matrix space. It is any map you can take. So in that set, maybe some of the image will not be an open in that. So let us give you an counter example for this question. So we'll write a note here. Define F from R2. So I'm taking the R here. R2 D1 and R2 D2 as F of X is equal to X for every X belongs to R, where D1 is a discrete matrix. And D2 is a usual matrix. The usual matrix means D of xy is equal to mod of x minus y for every xy belongs to R. So that is a usual matrix. And we have this map. And the previous example says that any map which is defined on a discrete matrix which will be continuous. So therefore we can say that here F is continuous on this R comma D1. Now we know that the singleton set X is open in R comma D1, but its image, that is F of singleton set X, the map is F of X is equal to X, so the image of this singleton set X will be a singleton set X, is not open in R with D2. With usual metric, this will not be open because the singleton set is not open, because if you draw an open neighborhood of this, which contains any open neighborhood of this, which contains lots of points other than this in a usual metric. So this will be not open in that. So this example tells you that the image of an open set need not be an open set. Okay. Now my next question is that if you have a function, so this is the question, if you have a function x to y, which is a continuous function, and f is 1 1 and on 2. Now question is f inverse continuous? That means if you have a function f, which is a function from x to y, which is a continuous function, and f is 1 1 and on 2, so there is no problem with the existence of inverse, because f inverse is exist if and only if it is 1 1 and on 2. So the question is, f is continuous, will it implies that f inverse is also continuous? The answer is no. Here also the answer is no. The example, what will be the counter example, is the previous example which we have stated here. The same example will work for this. So let's define a map f from r comma d1 to r comma d2 as f of x is equal to x. Okay, then we know that this f is continuous. We already discussed earlier why this is continuous. So we know that f is continuous. And this is then identity map f of x is equal to x. That means it is 1 1 and on 2 also. There is no problem with this is identity map. So it is 1 1 and on 2. So there is no problem for the inverse also. So we can also note that also this f is 1 1 and on 2. So therefore f inverse is exist. So now what is the f inverse of, or if I want to prove that or disprove that this f inverse of is not continuous, that is my objective. I'll to take for any singleton set is open in a discrete matrix, that is r comma d1, which we have considered. But the inverse image of this, that is f inverse of x, singleton set x, will be a singleton set x which is not open in r comma d2. With usual metric, this is not open. So therefore f inverse is not continuous. So which proves that if f is continuous, it does not imply that its inverse is continuous if it is exist. Let us discuss one more example here. Let us consider f and G, they are the two different continuous function I'm taking. So the next example, let F and G be continuous real valued function on a metric space X. Let A be the set of all points X belongs to X such that G of X is less than F of X. Then prove or disprove that A is open. So what is your answer? So let me write down what is this set first. A. First of all, it's given that F and G are continuous real valued function. That means F is a function from X to R which is continuous, and G is also a function from X to R which is a continuous function. So this is the condition is given. And what is the set A is there? The set A is set of all points X belongs to X such that G of X is less than F of X. The set of all points which are satisfying this. Okay, I want to prove that this whether this set A is open or it will be a closed or it is not open. So that is the objective of this. So what is your answer? What do you want to say regarding this? Whether this A is open or it is not open. So this is the set is given to you. So this set I can write down in this fashion. G of X minus F of X is less than, or I can write down this is less than 0. So this means that I can write down this is G of X minus F of X is belongs to. It says that is all the points which are smaller than 0. That means it is belongs to this set. Open interval minus infinity to 0. This statement I can rewrite as G minus F of X is belongs to minus infinity to 0. So this I can rewrite as all X belongs to this such that X is belongs to G minus F inverse of minus infinity to 0. So this is the actually set of all points in X such that set of all points in this. That means this set A is nothing but the G minus F inverse from minus infinity to 0. Now what is this set? Minus infinity to 0 is a open set that we can say. And what is f and g? They are given as continuous function. So since minus infinity to 0 is open in R with usual metric, and f and g are continuous on x to R. So we know that the subtraction of a two continuous function is continuous. So f minus g is also continuous. That we have here. Sorry, g minus f is also continuous. And this is open. So the inverse image of a continuous function is also continuous. Sorry, open. So we can say that g minus f inverse of minus infinity to 0 is open because it is open in X, because the inverse image of an open set under the continuous map is always open. That is the result we have discussed. So therefore we can say that this G or this set A is open in X, which completes the proof of that example. So if you have any doubt for now.